many problems in quantum mechanics involve systems with systems that are spherically symmetric. So in these cases, you have a Schrodinger equation that can be written in this way. Then you have a Laplacian. This is already the time-independent Schrodinger equation. Then you have a potential like this, V of R, and the energy, right? So now this term here, this would be the kinetic energy terms, right? So if you write it in spherical coordinates, this would be something like this. Then you have the Laplacian in spherical coordinates, that would be something like that. Let me write it with partial derivatives like that. Then there will be a term and the term for phi coordinate. This is what you get. And in many cases, for example, actually in any case where you have the potential, that depends only on the radial coordinates, not on the angular coordinates. So this is what defines a spherically symmetric system. So this is a potential that doesn't depend on theta or phi. So this is like, for example, central force potentials would be something like that. And in that case, you can separate the coordinates, and what you are going to find is something that here you would be able to replace this term here by something like L plus 1 over R squared, which then it would look like something like in the kinetic energy, it will lead to a term like H bar squared L plus 1 over R squared, right? And this has a negative sign here. And this would be a term that you can, there will be also 2m here. These are the constants that you get when you multiply this term here in that part. So in the end, you get something like these you relate to the eigenvalues of the angular momentum operator are L squared, and then you have now 2mr squared. And these would be the analog of kinetic energy of rotation, right? You have angular momentum squared over 2mr squared. So this is more or less how we interpret this thing. But this can be obtained from a separation of variables, like this thing that you can call L plus 1, and so on. This is something that we obtain from the separation of variables of this problem. So what we want to do here is, like, we say that this psi is a function of r, theta, and phi, but then we say that this is something like r, capital R of r, and then you have a function that right now I'm calling it y, and then you see why we call it like this later on. But then you have theta and phi here. Then in the end, you make this separation of variables here. I did this in another video for the specific case of the hydrogen atom, and if you want, you can see there how I did this thing there. But in the end, you have something like, in the separation of variables, you will have something like this: sine of theta, d theta. This is what operation over y, and then you have another term that is like this. Oh, actually, I just realized that I made a mistake here. This is not, the last term here is not a theta, it's actually a phi, of course, right? So this is the phi derivative here. So then this is what I'm saying that needs to be equal to a constant, right? And this is what I call like minus L plus 1, okay? Right? This could be any constant, but I'm calling it L plus 1, you see later on, because it will make my equation look like the equation for a spherical harmonics or for a Legendre polynomial equation. but it actually associated Legendre polynomial. But what I want to show in this video here is why this solution is a Legendre polynomial, associated Legendre polynomial multiplied by an exponential, which is also known as the spherical harmonics function. So how can I show that this equation that I get from the separation of variables in Schrodinger's equation, how can I say that this is really what I think it is, right? So let's do it like this. Actually, first thing to do here is to make another separation of variables. I want to work first with the coordinate phi. So then I will separate this like this, and phi like this, right? So if I make this, if I substitute this thing there, so the first step in the separation of coordinates is I make two functions multiplying, I multiply these two functions by each other, right? Then I substitute this thing into the equation, so what I have is like sine of theta. Then now I'm going to start writing these derivatives like this. And now I have only theta here, but phi doesn't need to be here because this is, I have a derivative only in theta here, right? Then the other term is 1 over sine squared of theta, and then theta can be here because I don't need to derive it. Now I have to derive only the phi function here. So and this has to be my constant. I'm going to start calling this constant A, and phi and theta, right? So next step is I divide everything by a multiplication between phi and theta. So when I do that, I can remove this thing from here. I end up with 1 over theta. I can cancel this. I end up with something like this, and I can cancel these two here. So here it's still not perfect because I have this sine of theta here, and then this theta, everything here is theta. But here I have theta and phi at the same term, so I cannot separate variables like that. But I can still multiply everything by sine squared. Then I have sine of theta as it is squared, then I cancel this one. Sine squared cancel this one. Then I have sine squared of theta in the other side here. Now I can find an equation where I have two terms and they have separated variables. I have like sine of theta something like that. Then I can put the other term there from the other side, like a sine squared of theta, and here I have plus 1 over phi, something like this, right? And this has to be equal to 0. Now everything here only depends on theta, while everything here only depends on phi. So this is a function of theta, and this is a function of phi. It's another function. But I'm saying that if I sum these two things, I have to find a constant, which is 0. So the only way this thing is possible is if I say that this thing is a constant, and this thing is also the same constant but with a negative sign. So just by convenience, I'm going to call this one minus m squared, and this one plus m squared. Of course, it can be any constant, but it's more convenient if I write it like that, because once I do that, now I'm saying that the phi function has to be something like 1 over capital phi. If I do it like this, then I get minus m squared. Then in the end, I have something like this, minus m squared phi. So now I have to find a function that if I derive 2 times, I find the same function but with a negative constant in front of it. So the solution for that is e to the minus, or actually e to the I m phi, and then m can be either minus or plus, it doesn't matter here. So I have to do it like that. But now actually m here could have any value, right? I mean, in principle, there is no, why would I say that this m here has to be anything specifically, right? It can be any number. But now I have to have specific numbers here. are actually integer numbers because of the fact that phi is a angular coordinate, so it has to obey some periodicity conditions, right? So I have to be able to say that phi of phi plus 2 pi is the same as phi of the angle without the 2 pi. So because of that, then I have e to the I m 2 pi e to the I m phi is equal to e to the I m phi. And then if I cancel these two things, then I end up with this is equal to 1, which is only true if m is equal to an integer. So that's why m cannot have any value. It has to be an integer. It's because of the periodicity of my system in the phi coordinate. So, okay, now I'm saying that this has an m squared term there. So now I need to go for the other part of my equation here. So in the end, I can rewrite this thing like this, right? Sine of theta then minus a sine squared of theta. This has to be a plus m squared, just plus m squared, and there should be a theta on the bottom here. Oh, I think I forgot to put it here actually, so there should be a theta here, right? Capital theta. So here's the capital theta. So I have to multiply everything by capital theta, then in the end I have the actual equation for this. So there will be capital theta here and capital theta here. Okay, so now let's rewrite finally the correct form of this. So this is the equation. Right now it doesn't tell me much, you know, but one thing that I can already do here, I can open this term here so that I can see what this leads me to. So one thing is I can find it like sine squared over theta, sine squared of theta. Then I have second derivative of the capital theta function. And the second term would be sine of theta, cosine of theta, and I'll have something like that. And this still doesn't look much with doesn't look much like something that I know, but I can make a substitution here that will help me. If I say that x is equal to cosine of theta, if I do it like that, then I want to have a derivative d dx of any function theta. In the end, this is going to be something like, or actually let's say d theta of the capital theta. That should be something like d dx of theta, dx d theta, and this will give me this multiplied by this derivative, that would be minus sine of theta. And then if I want a second derivative, these are the terms that I have there in the equation, right? So this is going to be there are going to be two terms here. One is cosine of theta, something like that, and plus sine squared of theta So these are the terms that I have. And also I can still say that if I find something like sine squared of theta, wherever I find this thing, I can rewrite it as 1 minus cosine squared, and cosine squared is x squared, right? I can do it like that. So let's start to substitute this thing here. So here I have sine squared. Sine squared I can already put as 1 minus x squared, as I said. Then I have second derivative of theta. Second derivative, I have a sine squared. So there will be again 1 minus x squared, second derivative. of theta, right? Then there will be a second term, which is minus cosine of theta, that's the x itself, and then sine squared, it will give me 1 minus x squared, and the first derivative of theta, this is just this first term here, okay? So this multiplied by this is what gives me these two terms that I just wrote. Then I have another one here, which is derivative of theta. This is going to give me minus sine multiplied by d theta dx. This is going to be then, I can erase this here and put a minus sign, and sine squared of theta, cosine of theta, I'm going to already write it like x, then d dx theta, right? Then this sine squared here, I'm also going to write it already like 1 minus x squared, right? Then what else? There will be this term here, which I can write as minus a sine squared. I can write 1 minus x squared theta minus m squared theta is equal to 0. That's my actual equation now. So these two terms, they can be put together, right? These two terms are the same, so it's going to be 2 times the same term. And I'm going to also to divide everything by 1 minus x squared. So this cancel this term here, and this cancel this, and this, and this, and there will be a 1 over 1 minus x squared in this part here. So in the end, what I get from this procedure is 1 minus x squared, second derivative, then minus, I have 2 terms like that, so 2x d theta dx minus a. Remember that this a in this page here, I defined this thing as something. It was minus l plus 1, right? So in the end, I can replace this number here again. It's going to be plus l plus 1, right? Just the theta, right? And minus m squared over 1 minus x squared theta equals to 0. So if you look in the literature, this equation that I just wrote here, this is exactly the form of the associated Legendre equation. So this associated Legendre equation, it's going to be solved by a Legendre polynomial, which is going to be a PL of m, PL and m, because you have like 2 things to think about here. There is this thing here and this one here, right? Two indexes to play with here, right? And it's going to be a polynomial, and you have the coordinate here will be x, which is actually cosine of theta, of course, right? And this is the solution for the theta part of your equation, right? This is what solves this one. But as I said, this is just one. This is just the theta part of the function. The actual function should be y of theta and phi, and this is this polynomial PML of cosine of theta multiplied by the phi part, which is e to the I m phi, and there will be a constant here. I mean, I cannot use this constant anymore because I already used this a somewhere else, so let's call it capital N. So there will be a constant here. So what we call spherical harmonics is this kind of function here, like a associated Legendre polynomial multiplied by an exponential, but with a specific number here that normalizes this function. So this is what gives me the actual spherical harmonics. So I'm not going to go into the details of how to obtain this n, but this is just a constant that normalizes this y. But let me already give you some information about what is the constraints between the L and the M. When you look for the solutions for the Legendre polynomials, the associated Legendre polynomials, you get something like this: PML of cosine of theta, right? Or you can rewrite it as P of ML of x, right? This is going to be something like, if you look for the Rodriguez formula for this thing, this is going to be proportional to a derivative of the actual Legendre polynomial, not the associated, but the actual Legendre polynomial, P of L of x, right? And this the derivative here will be made to the order of modulus of m. So if you choose m equal to 1, then you derive this 1 time. If you choose m equal to 2, then you derive it 2 times and 3 times and so on. If m is equal to 0, don't derive it. So that's the idea here. So what I'm saying here is that there is now a constraint in this thing, because you cannot take a derivative with an order to an order m that is larger than the order of the polynomial itself. So if you take this derivative like to m that is larger than L, then it's going to give you 0. So what I'm saying is, m in this approach here, m has to go from minus L to minus L plus 1, because it has to be integer, right? Integer. So minus L plus 1, minus L plus 2, and so on. And then you have 0, then you have L minus 1, and plus L. So it has to go from minus L to plus L only in integer numbers. And why is that? It's integer numbers because of the periodicity of the phi coordinate, as we discussed it in this part here, right? This one. And has to be integer because of that. And it has to have a limit at minus L and plus L, and that's because of the derivative that you take here when you want to find a solution for the associated Legendre polynomial, the associated Legendre equation, using the Legendre polynomials, right? You cannot derive this polynomial to an order that is higher than the order of the polynomial itself. So this is what explains for example, in the hydrogen atom, you want to solve the Schrodinger equation for the hydrogen atom. Then for the theta and phi coordinates, you get something like this. You get a spherical harmonic like that, right? Then you get solutions that are, let's say, L equal to 0, L equal to 1, L equal to 2. And this L equal to 0 allows you to use m equal to 0, m equal to minus 1, 0, or 1, m equal to minus 2, minus 1, 0, 1, 2, and so on and so forth. These are constraints that appear because of this definition here of the associated Legendre polynomials that will form your spherical harmonics. And this is something that you see in the hydrogen atoms, for example. So these solutions will be, for example, the orbitals of the hydrogen atom, like s orbital. That would be this one, right? This would be the s orbital, this would be the p orbital, and this would be the d orbital, and so on, right? So that's it.